Hello everyone. Today I thought what we would do is go over one of these quizzes I gave actually this semester over shear and moment diagrams. Alright, now this picture is out of a really old book, right? This is the book I used when I was in school, so it's pretty old. It's out of one of the Beer and Johnston books. I don't even know what version. But what we're going to do here is we're going to find the shear and moment equations as a function of x for these three sections. Alright, so we're going to have x going from 0 to 0.6, and then we're going to go 0.6 to 2.4, and then finally 2.4 to 3. And we're coming up with those regions because you can see those are the different sections here in between all of the loadings. Alright, so now we've got that. Let's look at these supports over here. Those of y'all that use the Hibbler textbooks and the Miriam-Craig books might not be aware of what those are. Those are just going to act like normal supports. All right, so those will provide a vertical force only. Okay, so keep that in mind. And that's why I have this little note here on the quiz. So first thing we want to do is I need to find what those normal supports are. So let's do that first. So this will be our first step. So we're going to get our external reactions. And to do that, we're just going to draw the basic free body diagram. All right, and then let's label the forces. Let me find a different color for that. Okay, so at A, we're going to have an AY. Let's just draw it going up. And then next to that, we have this 40. And then we're going to stay on the bottom here. So we got 40 again. We'll label the distances in just a second. And then at B, again, this is just going to be a vertical reaction. So let's put B, Y. And then at the top, what are we going to have? Well, I've got this distributed load. The intensity is 25 kilonewtons per meter. It happens over a length of 1.8. So we're going to do 25 times 1.8. And it's going to be right in the center of that rectangle. All right, so it's going to be right here. So here we'll have 25 times 1.8, and that equals 45. Units there will end up being, whoops, I put newtons, should be kilonewtons. Kilonewtons. All right, so we got that, and then we can label our distances. So from here to here is the 0.6. From here to here is 1.8, and then this is 0.6 again. Now I need to know where this is, right? This is right in the middle of that rectangle, so it's going to be right in the middle of the beam. All right, so whatever distance that would be, so 0.6 plus 0.9. So we'll have 1.5 there. All right, so now we have that. Now let's do our equilibrium equations. We only have two this time, right? Because I don't have anything in the x direction. So let's just go ahead and start with the moment equation. And I'm going to take the moment about B. All right, you could take the moment about A also. It'll give you the same thing in the end. All right, so the moment about B here, we're going to have negative AY times 3. It's negative because I said counterclockwise is positive. This would be a clockwise moment, making it negative. And then we're going to have plus 40 times 2.4. All right, so that's this 40 right here. It's going down, so it's counterclockwise, positive. Distance will be 1.8 times, or not times, but plus 0.6, which gives me 2.4. And then we've got this other 40. That's also going to be a positive moment, and that distance is 0.6. And then finally, I've got the 45 up here. All right, now that's going down, so that's going to be positive. And then the distance is going to be 1.5. All right, because remember, it's right in the middle. And then set it equal to 0. So now with this, I can go ahead and solve for AY. And we're going to get 62.5 kilonewtons. Okay, and you can probably already guess that BY is going to be the same thing, right? Because this is all symmetric. Everything's nice and symmetric here, but we'll go ahead and prove that by doing our force equation in the y direction. So we're going to have AY, which we already know is 62.5, minus 40, minus 40, plus BY, and then minus 45. Set it equal to 0. So now our only unknown here is BY. So we can solve. And BY then is just what we thought, 62.5 kilonewtons. All right, so now that we've got those external supports, we can start doing our sections and getting our equations for the shear and moment. All right, so let's start on the first section here. So that'll be right here. Okay, so this will be the region of X where we go from 0 to 0.6. And we'll just put a 1 here. Now we want to draw our free body diagram. Right, and I'm going to call this point C because that's where I cut the section. Okay, now we're only going to care about everything that's to the left of this line. Okay, so I want my force over here, which is the 62.5. Right, because that's AY. And then at C, I've cut it, I've sectioned it, so I need to look at my internal loadings. So the internal loadings that we're going to have here will be V and M. So V will be that internal shear. When we use this left side, you're going to put that going down. That way we have the correct sign convention for our diagrams. And then the moment, you should always draw it going counterclockwise if we're using this left section. All right. If we went for the right side, you would switch these directions. All right. But this is what we need to have the correct sign convention. And this distance here, let's call it X. All right. Now what we're going to do is just use our simple equilibrium equations. Whoops, I put X. This should be Y. There we go. We don't have an X, right? So, all right, and I'm going to say that going up is positive here. So we have a negative V plus 62.5. It's going to equal 0. So that means V is 62.5. So this is one of the functions that the problem was asking for. And we'll do the same thing for the moment. Now I'm going to take the moment about this point C right here. Counterclockwise will be positive. So we're going to have a positive M and then a minus 62.5 times the distance X. Set it equal to 0. So now for this section, M is going to be a function of X. So we'll have 62.5 times X. So that would be your equation for that section. So basically if you have an X value anywhere from 0 to 0.6, this value will give you V, so 62.5 will be your shear. And then your internal moment would be 62.5 times X. All right. Now let's do the second section. So it's going to be like in here. So we do the same thing. We're going to start all the way from A and go to this line here for section 2. And again, I'm going to call that point C. Now we need our forces. So we still have our force at A here, 62.5. And then we're going to have V and M, just like before. But now what else do we need to add? Well, now I need this 40, and then I have to worry about all of this, right? That distributed load that's going on. So let's add those in. So there's 40, and these forces are all kilonewtons. And then up top, if we look, this distance here is 0.6, and then this total distance here is X. So up top, when we do our distributed load, we need to know the distance the load's acting over. So the intensity is going to be 25, and then that distance that that load is acting on is going to be x minus the 0.6, because that will give me this right here. Okay, so now we're going to have that. And then now we're ready to do our equilibrium equations. All right, so forces in the y direction, we got 62.5 minus 40. We got minus v, and then we have the minus 25 times x minus 0.6. Set it equal to 0. So then now we can solve for v. And after you simplify this a little bit, you can expand out the 25 times x and 25 times the 0.6. Group up your terms. You'll get 37.5 minus 25x. So notice how when we have this distributed load, our shear is now a linear function of x. All right, before, when we were on this left side from 0 to 0.6, we just had a constant. All right, so it wasn't a function of x. So that's the difference this distributed load is going to make in your equations. All right, so now let's go ahead and do the moments about C. So same process we did up here. All right, we got a positive m, and we're taking the moment about this point here, so we're going to have a negative 62.5 times x. Then we have a plus 40. Now I need this distance here again, so we're going to do x minus 0.6. And then up here, I need to know this distance. All right, well that distance is going to be x minus 0.6 over 2. So that's going to give me a positive 25 times x minus 0.6. That gives me the force itself, and then the distance will be x minus 0.6 over 2. And that is it for that one. Set it to 0. And now we're going to solve for m. So remember, m is that internal moment. Now, once you expand all this out, I'm not going to go through all the algebra, but once you expand everything out and group up the like terms, you're going to have negative 12.5x squared plus 37.5x plus 19.5. All right, so now you have that. Now, if you look at these two, do you notice a pattern here, or a relationship, I should say? Well, what would happen if I took the derivative of m with respect to x? I would get v, right? Because I would get negative 12.5 times 2, which is 25. Then we have the x. And then here, if we take the derivative of this, we get 37.5. Just what we had here. Derivative of this one with respect to x is 0. So remember, your moment equation, if you take the derivative of that, you should get v. If you don't, you did something wrong. All right. And then likewise, you could take the integral of v and get a couple of the terms for m, but you wouldn't know what this constant is, right? So just something to keep in mind there. All right, so we got that one done. One more section. Let's do this one here. So this is for when we're at the right side of the beam. Now I'm going to go ahead and go all the way from the left over, just because that's what I like to do usually. All right, so V is going to go down. We have M. And then now at this point, we have passed the distributed load, right? So we're not cutting that in the middle anymore. We're all the way to the right of that. We are still going to have our A y over here, which is 62.5. We got the 40. We have the other 40, because we're to the right of that. And then up top, I'm going to have just the full distributed load, which was the 45. And this full distance here is x. All right, so that means that if this was 1.5, that this here will be x minus 1.5. All right, and that's 0.6, this is 1.8. Okay, so y'all know the drill here, equilibrium equations. All right, so forces in the y direction, going up is positive. So we have our 62.5 minus 40, minus 40, we have the minus 45, and then minus v. All right, so now we simplify all of this. So v then is going to be negative 62.5, and that's going to be kilonewtons. I've been not putting my units here. Everything's either kilonewton meters for the moments or kilonewtons for v. And let's do our moments about point C. All right, and for this one we're going to have negative 62.5x plus 40 times x minus 0.6, right, because I need just this distance from here to here. Then for the next 40 kilonewton force, the distance will be x minus 2.4, because 0.6 plus 1.8 is 2.4. So if I subtract those, I get this distance here. And then we need plus 45 times x minus 1.5. And I almost forgot one more thing. We need plus m. So now let's solve for m. And after you group up your terms and everything, you're going to get negative 62.5x plus 187.5. All right, so that's what we have for this one. And this is kilonewton meters. Notice again, you take the derivative of m, you're going to get v. All right, so notice that relationship. Okay, so now we have all of this. We're ready to actually do the shear moment diagram. All right, so let's get this piece of paper out and we'll kind of work our way through this. Now, after we're done doing it this long way, I'll show you how to do it the graphical way, and it'll be a lot quicker. Right, the graphical way is always quicker than this long way. But sometimes you do need these equations. Okay, so what we want to do first when we're drawing our shear and moment diagrams is you want to draw a picture of the original system with all of the reaction supports denoted on here. They need to be drawn in the correct directions. So if up here, when we were finding AY and BY, if one of these or both of them would have been negative, we would want to show that on here. So instead of going up, I'd want to go down, right? So it shows the correct direction. That'll make it easier. And then we've got 40, we got 40, and then over here we got 62.5. And then up top, you want to actually show the distributed load. All right, and this is 25 kilonewton per meter. And let's put these distances up here also. Okay, now below that, let's put V. And then we have X. Units here will be kilonewtons. And then we're just going to start working through our different equations. So for V, for the first section, we're going to have 62.5. All right, so this is going to be our value for V until we get to that 0.6 and beyond. All right, so that means let's start up here. We're going to be at 62.5. And right below where that 40 is, you'll stop. Okay. Now, what we need to do is, we'll do the moment diagram in just a minute. Now let's jump to the next V equation. So now we're right here. All right, now this is a linear function. It's got a negative slope, so it's going to be like that. And what we need to do is know where that's starting. So what you would do is plug in the 0.6. And here I did it on my calculator. So you can see we took that expression, 37.5 minus 25x. I plugged in 0.6 for x, and we get 22.5. So that means we're going to drop this shear diagram down to 22.5. All right, so now we've got that. That's our starting point, and then from there on, we're going to use this linear function, and we need to know the final value. So the final value, what would that be? Well, the final value, I'll put it in here, is going to be that same expression, 37.5 minus 25, but now you need that final value of x for this section 2. All right, so that's going to be where we're at 0.6 plus 1.8. All right, so put that in for x. That's going to give us negative 22.5. All right, so that's where we're going to be right below this 40. We're going to be at negative 22.5, and we have that linear function with that negative slope, so it's going to look like that. Okay, now we go to the next equation. So notice it's at negative 62.5. So that means we're going to drop down, and I'm going to draw over my 22.5 here, but we're going to go down to negative 62.5, go across, and then you're going to bring it back up to that x-axis. All right, so this would be our shear diagram. All right, now this location right here, notice this is where shear went to 0, right? We need to know where that is because that's going to tell us something for our moment diagram. So we want to figure out where that is. Now the easiest thing you could do here to find this location, let's assume this is not symmetric, is to use your equation for V for this section. So we're using section 2 here, so 37.5 minus 25 times x. And we want to set it equal to 0, solve for x. And if you do that, you're going to get 1.5. All right, so this distance to here is 1.5 meters. All right. So now we've got that. And then with that, we're ready to go to our moment diagram. And units here are kilonewton meters. So first, we'll start with this top one. So negative, or not negative, but 62.5x. Now we need to know where to go, right? So the end of this section is at 0.6 for x. So we're going to do 62.5 times 0.6. Gives me 37.5, right? Now, that's a linear function, positive slope. So we're going to go up to like right here, and let's put 37.5. Right? So now we've got that. Then we go to our next equation. And it's getting hard for me to show you all these equations. So now this is the next one. We have this quadratic. All right. Notice it's got a negative here. It's quadratic. And on this one, if you want, you can put in the 0.6. See where it's going to be. So let's do that. And then we want to add the 37.5 times 0.6 and then add the 19.5. So that's going to be at 37.5, right? So that's right where we are already. So we don't need to jump up or anything. But now we need to know our final value. So let's do our final value. And remember, x is going to be 0.6 plus 1.8 at this point. So we're going to do 2.4 for x, all right? So negative 12.5 times 2.4 squared plus 37.5 times 2.4 and then plus 19.5. So we go back down to 37.5. Now remember, this is quadratic. And on your diagram, your peak for the quadratic function should line up where v crosses 0 here. All right, and then we're going to end up back over here at 37.5. So that'll kind of give you some guidelines for your drawing. All right. Now you always want to put the value right here at the peak. Any ideas how to do that? Well, what we're going to do is take the moment equation right here, plug in x equals 1.5. All right, so that's what we'll do for that. And we'll write that one out. So if you plug all of that in, we get 47.6 approximately. All right, that's kind of rounded, but that's what you'll get for that max point. All right, and then that's the end of that second section. Now we go to the next one. Linear, negative slope here. If you want, you can double check, make sure it's starting in the same place. Remember, x is 2.4 here. So we'd have negative 62.5 times 2.4. Whoops, I didn't do the 62.5 right. Plus the 187.5 gives me 37.5. That checks out. And then we want the final value. So the final value is the 0.6 plus the 1.8 plus the 0.6. So 3. All right, so we're going to do negative 62.5 times 3 plus 187.5, which takes me to 0, which is what we should get, right? So if you don't end up at 0, you've done something wrong. So that means we're going to go down here and end at 0 right there. And then this would be your diagram. Okay, so that is how you would do it with the equations that are a function of x, right? So you go through, look at each of the sections, get equations for v and m as functions of x, and then basically you just use those to do your diagrams. All right, that is the long and tedious way of doing things. All right, but like I said, sometimes you do need those equations. The easier way is to do this graphically, just by looking at the actual picture. So let's do that next. All right, so let's do this graphically now. So this is what we had before, right? So we had our shear diagram, we had this moment diagram, and we had that as our original system. So we're going to start out by drawing this again. So before you do the graphical method, you still have to have the external reaction supports found, so you still do that same first step. But doing it this way, graphically, we can avoid having to get all of those equations for v and m for each of the different sections. So basically, we'll just look at this and get our shear diagram, and then we'll be able to use the information from the shear diagram to get the m diagram. So it's a lot quicker than doing it the other way. All right, so let's go ahead and I'm going to use a different piece of paper, but let's go ahead and redraw this top diagram. All right, so we had that, and then we have the 62.5, we got 40, and then 62.5 again. And then now we can put the distributed load up here on the top. And we need these distances, so let's put those. Okay, so now we've got those distances, and we're ready to go. Okay, so let's do shear first. You always want to put the shear diagram first because we're going to use the shear diagram to get the moment diagram. All right, now anytime we have an applied force that's pushing up, we're going to jump up on our shear diagram. If it's going down, we're going to jump down on the diagram. All right, for the distributed load, if it's pointing down, that is a downward motion on the shear diagram. If it were pointing up, we would go up. Okay? And all this information is in the class online. So if you've enrolled in that, you've seen all this information. Okay, so let's go ahead and let's jump up 62.5. Right here. Now notice there's nothing going on in between these two forces, right? So we're just going to draw a straight line until we're right below the 40. Now we've got the 40 here, it's pointing down, so we're going to jump down by 40. So that's going to take us to 22.5 right here. Okay. Now we also have this distributed load. I can't forget about that. So we need to deal with that. Now, if we have a uniform distributed load, that means we're going to have a linear V function. All right. And we saw that when we did the equations, right? Because if y'all remember, the v equation for this section was a linear function. So anytime it's uniform, you're going to get a linear v function. It's pointing down, so we're going to get a negative slope. All right, so it's going to have this direction like that. Okay? And the amount you're going to drop down is going to be found by basically finding the area here. All right, that's how I think of it. So we're going to do 25 times the length, which is 1.8. All right, and what does that equal? That is 45. All right, so that's the amount of the force that you get from the distributed load. All right, but this 45 is going to give you your delta V, so it tells you how much you need to change your value of V by. So if we do 22.5 minus 45, we get a negative 22.5. So that will be our V value when we get to the end of this section. All right, so we're going to go to negative 22.5. And it's going to be a linear function just like that. All right. Now, we've taken care of this, but now we've got this 40 here. So this 40 means we're going to drop down by 40 again. All right, so if I do negative 22.5 minus 40, I get negative 62.5. So that takes us to here. Nothing's going on right here in between these two forces. So we draw a straight line over, and then at the very end we have a positive or an upward force of 62.5. So that means we're going to go up back to the x-axis, because negative 62.5 plus positive 62.5 takes us to 0. All right, and so then you get that shear diagram. All right, so not too bad, right? Easier than the other method. All right, now the next part here is to find this location where V goes to 0. All right, now looking at this problem, we can tell where it is, right? Because this whole thing is symmetric. So we know it's going to be right in the middle. My diagram doesn't show it right in the middle, but it will be. So this is going to be x equals 1.5, because remember the total length is 3. So we know it's got to be at 0 when x is 1.5. But you won't always have the case where you have a symmetric system. So if you don't have a symmetric system and you're going to do it the graphical way, there's a couple of things you can do. You can go ahead and do the free body diagram using the method that we did before, right? You could go ahead and do this method here for just this one section and get this equation. All right, so that's one way. That might be an easier way for you. Or the other way is you can get the equation for this line and do it that way. All right, so I'll show you how to do that in case you want to use it, that method. All right. So if we find the equation of the line, you know we have y equals mx plus b, because this is a linear function, right? So in this case, instead of y, we're going to have v. And the slope, we can find that because it's rise over run, right? So you can easily find the slope of this. So m is going to basically be the 225 minus the negative 225. And then put it over the run, which is 1.8. And what's that going to give us? Whoops, actually just make that positive. All right, so it's going to give us 25 for that slope. But we know it's negative, right, because it's going that direction. So we'll put negative on there. So we have that. That says direction there. All right. And then the only other thing we need is this b. All right. So I have two endpoints. I have 22.5 when x is at 0.6. And then I've got negative 22.5 when x is at 2.4. So you could use those data points to get b. All right. So let's go ahead and look at those. So let's just put it x is 0.6. V is 22.5. when x is 2.4, v is negative 22.5. So that means using this expression right here, where remember y is going to be equivalent to v, I could say negative 22.5 equals the slope, which is negative 25 times x plus b. Now, for this value of negative 22.5, x is going to be 2.4. So b then, if you were to go through and solve that, will be 37.5. All right. So then that gives you your expression for v as negative 25x plus 37.5. So you could take that equation, set it equal to 0, and solve for x. And you'll get 1.5. All right. So a couple of ways to do that. First of all, always check for symmetry. That's the easiest thing to do. If you don't have symmetry, you can come up with the equation for this line or do the free body diagram method we did earlier. Okay. Now that we've got that done, let's go down to M. Units here are kilonewton meters. First thing you want to do is make sure you don't have any applied moments. All right. We don't have any applied moments, so I can forget about looking at this diagram now. We're going to focus in on the shear diagram. And what we want to do is find the area of the region under or below the shear curve, because that's going to give me my delta M. All right, so let's do this one first. So let's find the area of this rectangle. So that'll be 62.5, and then this length here is 0.6. What does that give us? Well, let's see. That'll be 37.5. Right here is a triangle. You can see it right here, triangle. All right, find that area. So we're going to have 1/2. The height there is 22.5. The base is going to be 1.5 minus 0.6. All right, because that'll give me from here to here. So that ends up equaling 10.125. All right, next we come over to this one. So this is like a triangle. And let's put it over here. So A for this will be 1/2. We got 22.5. And then this length right here is going to be what? It's going to be 0.9. All right, so now we got 0.9. And then we need this rectangle. First, let's put this value. This is going to be 10.125 again. And then this rectangle right here, that area, 62.5, because that's that length, right? 62.5. And then the width here is going to be 0.6. So that takes me to 37.5. Okay, so these values here are what we're going to use to draw our moment diagram. Now, those are our delta M's. Okay, so we're going to start on the left. We have 37.5. So I have to go from 0 to 37.5. And this right here is a positive V. We have a uniform line here, right? It's just constant. So that means I'm going to have a linear function for the moment. All right, so we're going to go to 37.5 right there. Now, I know this is going to be linear because this is uniform. And remember, we have that relationship that if you take the derivative of M, you get V. Okay? So in order to get a constant, we have to have a value times x down here. Next, we go to this triangle. So this is 10.125. All right, so that's our delta M. So you're going to take 37.5. Oops. We're going to add to that 10.125. We get 47.6, which, if you notice, that's what we had before. All right, so that'll take us to the top of the quadratic curve. All right, because if we have a linear curve here, on the shear diagram, I have to have a quadratic on the moment diagram, right? Because I have to be able to take the derivative of m to get v. So I have to have x squared to get just an x for v. All right, and then next we get this next triangle, 10.125, that's our delta. Now this is a negative v, so I know I need to go down on the m diagram. All right, so we're going to have 47.6 minus 10.125, so 37.5 approximately. So let's come back over to here. All right, and then last thing, 37.5. All right, that's the area. So this is uniform. We're negative v, so that means we're going to have a negative slope for m. And the delta m is 37.5. So if we're starting at 37.5, we subtract 37.5, I'm going to end up at 0. Okay, and then there is your diagram. All right. So this gives you an easy way to go ahead and draw the diagram once you have your external forces found. All right. So this is just kind of an overview. On the class online, you know, we go through a lot more details on how to do all of that, and we have a lot more examples, but hopefully that'll get you started if you're not sure how to do the graphical method. All right, you guys, so I will see y'all next time. You guys have a great day.